Okay. Welcome everyone. We are glad and excited to have Lars Rohwedder today. He is currently a postdoctoral researcher at EPFL Switzerland, and before that he has received his PhD from University of Kiel, Germany, where he was the recipient of the PhD of the Year award. He has produced several exciting results in recent years, especially in integer programming and scheduling. Today he will talk about his breakthrough result on preemptive weighted flow time on a single machine, and it was a long-standing open problem to obtain a constant approximation for this problem. Recently, we have seen a lot of progress in this problem. First, Batra, Garg, and Kumar gave a pseudo-polynomial time constant approximation in Fox 2018. Then Feige, Kulkarni, and Lee presented a constant approximation in Soda 19, but the constant was really large, more than 10,000 or something. But finally, this year's talk, Lars and Andy showed a 2 plus epsilon approximation for the problem, and we are really excited to hear about that. So Lars, welcome, and it's all yours now.
Thank you very much for the nice introduction, and let me just share my screen. Do you see everything?
Yes.
Okay, great. So you already gave the topic away. So this is a recent collaboration with Andy Wiese. He has been at the University of Chile at the time, but now he moved to Amsterdam, and this work appeared on this year's stock. So I will first introduce the scheduling problem we will work on in this talk. So in this problem, we're given a set of jobs. Each of them has a processing time Pj and a release time Rj. So we only have a single machine, and we need to process these jobs all on the single machine. We can only process a job after it's released, and we can interrupt it if we want. For example, the red job is interrupted by the yellow job. But in total, every job has to be processed for a time that corresponds to its Pj value. And of course, at each time, there can only be one job that is processed. So if you're given such a schedule, you can determine what is called the flow time of each job. This is the time that a job spends from being released until it's completed. So for example, here the blue job has a very small flow time, which only corresponds to its Pj value. The red job has a very large flow time because it could not be processed immediately. It was interrupted by this yellow job. And of course, flow time is a very natural criteria to optimize for. And since there are multiple jobs, we have to decide on some trade-off. And a very well-known objective is to minimize the weighted sum of flow times. So each job, in addition, is given some weight, Wj, which describes how important it is, and then you simply want to minimize the sum of weight times flow time for each job. So this, for example, generalizes another natural objective, which is to minimize the average flow time. And so, like Arundam already said, this is a very fundamental scheduling problem that has been studied quite a lot recently. So there have been studies in online setting with multiple machines, with speed augmentation, or in other special cases where the weights have certain forms. But even in one of the most fundamental settings, which I just introduced, with a single machine, and in the offline setting, so we know everything up front, the approximation rate that you can achieve by a polynomial time algorithm has been quite a mystery for a long time. And this was, for example, noted in the survey of Schurman and Wuginger on the most important questions in scheduling 20 years ago. So Fortunately, there's been a lot of progress recently, and this maybe started with a work by Bansal and Proust, who used some very nice geometric ideas and LP rounding techniques to obtain a log-log n approximation algorithm. Then 3 years ago, Batra, Garg, and Kumar gave the first constant approximation, but this constant was huge, like greater than 10,000. They didn't optimize for the constant. It was more important that it is any constant. And Andy and I were now able to greatly improve on this and give a really small constant, only a 2+epsilon approximation. And there's two other works that I want to mention. So already 20 years ago, Chikuri and Kana, they showed that there's some kind of Q-peters for this problem. So you can approximate it arbitrarily well in quasi-polynomial time. But the step towards a truly polynomial algorithm was actually very complicated. And one result that I implicitly used in all of the above is that an important work by Feigl, Kulkarni, and Lee 2 years ago showed that you can basically turn any pseudo-polynomial algorithm into a polynomial time algorithm with a very, very small loss in the approximation guarantee. So basically, you can assume that all numbers in the input are polynomially bounded. And this assumption I also used in all of these algorithms. So also the algorithm by Chikuri and Kana, for example, it had a large dependency on the largest number in the input, but using the result by Feigl, Kulkarni, and Lee, you can actually get to the true Q-peters. And our result, it also uses this pre-processing that all numbers are polynomial bounded, and it relies on a lot on the previous work by Batra, Garg, and Kumar. So I will try to point out throughout the talk a little bit where the differences between our work and theirs lie. So we will start off with an integer programming formulation of the problem. And don't worry, this is a lot of math for one slide, but we will not go through all of this because we will take a very geometric look at this integer program. And I'll instead explain it with this picture below. So in this picture below, I have sorted all the jobs by the release time, and I arranged them in these rows. So the first row, it corresponds to the job that was released first, and the last row corresponds to the job that was released last. And the columns here, or the x-axis, corresponds to the time. So each column is 1 unit of time. Because of all this pre-processing, we can assume that basically the time is in discrete steps. Everything is small. So each of these squares here is it corresponds to a job and a point of time after the job has been released. This is also why these rows start in a monotone order. Now, the hard part about solving the scheduling problem is to determine when each job is finished. So if you know in the optimal schedule, from the optimal schedule, what the correct completion times were for each job, then computing the schedule is actually polynomial time. So what we want to determine is, in some sense, how long does every job stay alive, and this corresponds to like selecting a prefix of each of these rows. And this is like in this integer program up here. Here we have a variable for each of these squares, and we have a constraint that says, okay, if so we start with ones, and at some point we drop to 0, and then we stay at 0. So the variables and this last constraint, they basically model that we want to select a prefix of each row. But of course, there need to be other constraints to make sure that after we determine these prefixes, we can actually compute the schedule. So in some sense, we don't want to, we cannot complete every job immediately. We have to make sure that the machine is also capable of processing everything. And this is what this complicated first constraint says. So we don't need to understand why this is, but this is a constraint that actually ensures that if I choose the variables such that they satisfy these constraints, then I can recover a schedule that also completes every job within this time that we determined. But these constraints that we have here, they have a very nice geometric interpretation in this picture below, because they actually correspond to some kind of vertical rays. So what I'll explain in a second what I mean by this. So if we look at one of these constraints, so we have actually one constraint for every S and T, for these are time units of time. And if we focus on one of these constraints, then the left-hand side here, it corresponds to jobs that intersect with a vertical ray. So you see there's on the left-hand side, we always sum over a set of xjt variables multiplied by pj. And they all share the same value of t. So we already know that the left-hand side, the support of this constraint, it lies on the same column. And actually it has even this monotone property that these are exactly variables corresponding to like a vertical ray, like this. So for this vertical ray, for example, we would sum up over the first job, the pj value of this. Then we would not sum over the second job because the prefix ends before the ray, and we would add the fourth job. And this sum, well, the constraint says that this sum has to be greater or equal than some right-hand side. We just treat this as some number that we derive from the ILP. But using this interpretation, we basically come from the scheduling problem to a very, very different geometric problem. So the problem, in order to solve this scheduling problem, it is enough to solve this problem where we select like horizontal prefixes such that these vertical demands, these rays, are all covered. And the cost that we want to minimize, it's some linear function in the length of these prefixes. So each prefix, we pay the weight of the job for times the length of the prefix. So we have some linear function in the lengths of the prefixes that we want to minimize, and we want to cover each of these constraints which are given by these vertical rays. But
one question. So here, what is preemption?
What was that?
So where do you use preemption in the inequality? Where do you ensure allow preemption?
So this constraint, it is only sufficient if you allow preemption. So if you solve this ILP and you do not allow preemption, then you're not guaranteed that you can find a schedule which satisfies these completion times. But if you allow preemptions, then this constraint, it's sufficient to guarantee that there exists a schedule.
Okay, thanks.
What does the decision variable pj represent? Like say in an x
This,
is
sorry?
kind of it makes sense. It has a fairly direct interpretation. But what does pj? So pj, I'm presuming, is also a decision variable. It's an unknown in the ILP.
No, so the PJ comes from the problem instance. So in the problem instance, each job has a processing time PJ and it has a wait WJ and a release time RJ. So these are values from the input. So for example, the wait goes into the objective function, and the PJ value, it goes into this covering constraint. Now, I understand it's not obvious why this ILP models the problem that I just introduced, but we will just, I just need you to believe me that it does. And so this models our problem, and it has this very nice geometric interpretation. Okay. So in order to solve the scheduling problem, we will instead solve this geometric problem where we select prefixes over every row, and we want to cover these demands of the vertical race. But especially these prefix constraints, they actually make it very complicated. So our first step is to further simplify this geometric problem by trading this prefix constraint for a different constraint. So instead of saying I need to select a prefix of every row, we will group the squares in every row in this geometric way, so in some exponentially growing intervals, and we will say of every such group you have to select all these squares or none. So and the cost of each of these groups or rectangles is then just the sum of the length. So the a prefix here would cost wj times the length, and this is the same. We use the same cost here for these groups. So it's easy to see that with these group constraints instead of the prefix constraints, we just lose a constant, because suppose you have some solution that satisfies the prefix constraint, or it is actually a prefix of this row, then of course we can just round up to the next end of a group. This increases the cost at most by a factor of 2, and the whole solution of course stays feasible, because we are just adding more elements to the solution, and since we only have these covering constraints, adding something cannot be bad. So if we have a solution which satisfies the prefix constraint, we can also derive a solution that satisfies these group constraints. On the other hand, if we have a solution that satisfies these group constraints, so every group is selected completely or not at all, then we can also derive a solution that satisfies the prefix constraint by just filling up all these holes. And all these holes together are they cannot be longer than the last group here. So again, this just increases the value of the solution by a factor of 2. So if we have a solution with these group constraints, we can recover a solution of slightly worse value for these prefix constraints. So that way we can trade these prefix constraints for these group constraints, which are easier to handle later on. And there's one more complication that we want to avoid. So if I do this geometric grouping for the next job or the next row, then of course I can get these very complicated intersections where neither of the two is a subset of another. They may have a complicated intersection. And Batra, Garg, and Kumar, they actually show that you can use a slightly more involved geometric grouping, which has much simpler intersections. So you still want that the groups grow exponentially, but you can make sure that they have this kind of nice hierarchical structure, so that if I have a group here, then the groups below, they basically cut the group both in two halves. Or it can also happen that it is again the same group, but you basically have this tree-like structure, and to obtain this, you may lose a factor of 32 in your approximation ratio. So if you can solve the problem with these nice hierarchical groups, you will also get a constant approximation for the scheduling problem. Now, since we are aiming for a 2+epsilon approximation in the paper, we are adding some more technical tricks here. So what we do, in fact, is that we take each of these groups constructed as in the previous slide, and we cut it into a constant number of subgroups, and we require that of these subgroups you select a prefix. But each of these groups are independent. Now, this, of course, is a much less clean problem, but if you reduce to this, you need to lose only a factor of 1+epsilon, so basically at a negligible cost you can reduce to this problem. And everything that I will explain later on in the talk, it still works for this problem as well. So, but for the purpose of this talk, I will go back to the clean problem that we had before. And let me just quickly recap what the problem is. So
what is the advantage of removing the prefix constraints? Is it because the number of constraints are too many, or so?
So we want to solve this problem later on in a kind of dynamic programming way. So, and here this tree-like structures of this group, these groups, it helps us to build like a natural dynamic program to solve this. So this has this very nice hierarchical structure where we can use dynamic programming, and this just doesn't work if you have these prefix constraints. So this is why we want to have the group constraints instead.
If you have the prefix constraint, then the runtime becomes a quasi-polynomial, or what happens if you use that from there?
No. The approach that I will explain to solve this, it just doesn't work with the prefix constraints. You need this kind of hierarchical structure of these group constraints in order to solve it.
Okay, thanks.
So let me briefly recap what we want to do. So we have these nice hierarchically aligned rectangles, and we have these constraints given by vertical arrays. Sorry, there's some background noise. I'll just close the window. Sorry for the interruption, there was some construction going on outside. So we have these rectangles, we have these arrays, and we want to select a subset of the rectangles, and this subset should cover each ray. And for each ray, we will look at only those selected rectangles that intersect with the ray, and the sum of their weights should be greater or equal than the demand of the ray. And in addition, each of the rectangles has some cost associated with it, and this we want to minimize. So if there are any questions about this problem, now is a good time to ask. Okay, if not, then we will continue on the approach to solve this kind of problem. And yes.
Question. So the weights that every vertical ray has also, I mean, it's quite well structured. Right? It's the right hand side of the inequality that you, or you're going to assume that doesn't matter. It's just
yes, so the demand of each ray, it has a specific form derived from the ILP, but actually to solve this we will not make use of that, so we will just say it is some number that we have to cover, and maybe you can improve something if you use that this has a certain structure, but we will not make use of any of that.
If I just kind of very naively think of it, this is like a set cover kind of a problem. You have, and so of course, like that's like a log n approximation completely defeats your purpose. But at this point, you have reduced it to a set cover problem.
Yes, that's right. Kind of set cover problem with a lot of structure. Yes.
In like, yeah, this structure. Okay.
And so maybe let me briefly make some connection to the previous work by Batra, Garg, and Kumar. So they use a similar approach, but they work directly on like this tree structure that you get in this kind of instance, and not so much on this two-dimensional visualization. And if you translate their problem that they get, they actually get demands which are not vertical rays, but vertical lines that start with somewhere and end somewhere. So they get this more complicated problem. So it's much harder to solve if these vertical rays were to end somewhere, which is not the very bottom. And one of the nice observations in our paper is that these constraints actually have this form that the constraint goes all the way down, and this allows us to simplify some of the arguments, and that way also improve the approximation rate at other parts. So I'm really sorry about the background noise. I hope it's not too bad. Anyway, so
this is, when you say these are going all the way down, it means that it intersects with all the jobs that are sort of in like lower rows. Is that?
Yes, except when they are released after the ray, right? For example, this middle ray, it does not intersect with the last drop, of course. But in some sense, what we will make use of later is that instead of selecting this rectangle, you can also select the same rectangle at a lower place in some sense, if they have similar weight and cost. So, like selecting something down, more downwards is always better than selecting something up. And this is a property that you get because these vertical arrays, they go all the way to the bottom. So in order to we take the rough idea of solving this problem is very simple. We first take our optimal solution where we show that given this optimal solution, you can construct an approximate solution which has a lot of structure, which is very simple. And then our goal is to compute only this very simple approximate solution. And because this approximate solution is so simple, it allows us to guess parts of the solution. So we cannot guess the whole solution, but we can guess certain parts of it. And then using dynamic programming, we can later recombine these parts to recover the overall solution again. And in the following, I will actually start in a reverse way. So I will first explain the idea of the dynamic program so that we will see what we actually need in the properties of this simple solution. And so let's start with the dynamic program. We will first fix one unit of time, and we will look at all the rectangles that intersect with it. And these rectangles have this very simple structure, right? There is some group of rectangles which have exactly only this point of time in them. Then there's some bigger group which contains these lowest level rectangles, and then there's again some bigger group, and this continues. So these are all rectangles that are relevant for this unit of time, or put differently, these are all rectangles that are relevant for all covering constraints, all vertical rays that have this x coordinate. And we will just assume that we have this magical oracle that we will develop later on, which gives us some guesses for this part of the solution. So all rectangles that are relevant for this unit of time. So this looks something like this. The apple, for example, it corresponds to some subset of these topmost rectangles. This apple corresponds to some subset of these. The lemon, some subset of these rectangles. Another guess for this solution might be that the first group we want to select a different subset of these rectangles. So these are like three different guesses of how the solution on this part, on all rectangles that intersect with this unit of time, could look like. And we assume that the number of we have this magical oracle which gives us a small number of guesses, a polynomial number of guesses, in which one of them corresponds to the solution that we look for. So especially these are not all subsets of these rectangles, this would be far too much. But only like a specific structured set of subsets, such that we can guarantee that it's still polynomially bounded. And we can, of course, we first ensure that for all these guesses, the constraints on this unit of time, so all the vertical rays that have this x coordinate, that these are feasible for the guesses. Otherwise, it cannot be the correct guess. And we have this oracle, and we will look at the adjacent unit of time, and the oracle will also give us some guesses for how the solution looks like on these three parts. So notice that the first two parts, they are identical in both, or these are the identical rectangles in left and right, and in the last layer, these are different sets of rectangles. So these might be some guesses for the red unit of time. And to recover now a solution for both time units, we must make sure that our guesses are consistent. So, for example, this solution that we guessed, apple, apple, cherry, it could be combined with this apple, apple, lemon, because they both agree on the first two parts. So this is like a valid candidate for the solution corresponding to these two time steps. On the other hand, apple, lemon, banana cannot be a correct guess because there's no corresponding guess in the right in the green unit of time. And similarly, apple, orange, banana does not have a counterpart here. So given this, we will end up with like two guesses that survive. For these two time units, the solution could either look like apple, apple, and then on the left cherry, on the right lemon, or this other guess. And we will again do the same thing for the next two time units, and we might end up with these two guesses. And again, we will look at, can they be recombined together? So in this case, they have to agree on the first part of the solution, because again, because now the second part is actually disjoint. So for apple, we don't have a counterpart on the other side. Likewise, for lemon, we don't have a counterpart. So we know these cannot be our correct guesses. And the solution that the only consistent solution that we can produce is this one starting with cherry, raspberry. But and of course, if we have multiple options, we will always take the cheaper one. And this way, if we are given this great oracle which guesses these parts of the solution, then we can recombine them in a bottom-up fashion to recover like the actual solution they came from. So now let me talk about how this magical oracle looks like. And we will first focus on a simpler task of just guessing a solution or an approximate solution for like rectangles that all look the same. So just vertically shifted copies of the same rectangles, although they might have different costs and different weights. So we will first group these rectangles by the density, which is the cost divided by the weight. So in some sense, a measure of how good the rectangle is. So let's say we have expensive rectangles and we have cheap rectangles, in the sense that the cost divided by weight ratio is low or high. And if we round the costs by a
Lars,
factor.
so what is cost here? Sorry to interrupt, but like cost is the demand they are satisfying, or the weight is WJ, and or like the powers of
Yes,
what
so
is cost here?
the costs they come from like you said, cost and weights are derived from the ILP, but you can also now just think of every rectangle having some cost which you have to pay for taking it in the solution, and it has a weight which is used to cover the rays that intersect with it. And well, the cost, it comes from this might be a bit confusing, because the cost comes from the weight in the scheduling problem, and the weight is actually comes from the processing times in the scheduling problem. But for now, maybe just think of the geometric problem and say that every rectangle has a specific cost and a specific weight. Okay. So if we round the costs a little bit, then we can make sure that there are only logarithmically many of these density groups, because in the beginning already we assumed that all the numbers are polynomially bounded, and increasing the costs by a factor of 1 plus epsilon, it also increases the cost of the optimal solution only by 1 plus epsilon. So we can assume at a very small cost that these ratios, there are just log n many of them. So in this example, let's say there are just two. There's a cheap density and an expensive density. Now, let these gold bars, they correspond to the actual costs. So the color is the density, like cost divided by weight, but these gold bars correspond to actual cost. So the uppermost rectangle costs 1, this costs 3, 5, and 2. And we will now simplify the solution for each of these densities independently. So let's say opt selects these upper two blue rectangles. So that means opt pays in total 4 for these blue rectangles. And we will now build a simple approximate solution as follows. We will throw away all rectangles that are greater than opt's budget, because well, they can also not be used by opt, so they are not relevant to us. We will now start with the lowest rectangle and greedily buy all rectangles starting from the bottom until we exceeded the budget of opt. So opt paid 4 in total. So after taking the the lowest rectangle, we paid 2. Then the next one we ignore, and the third one, it adds up to 5. So we exceeded opt's budget and we stop here. And we do this kind of greedy shaping of the solution for each of the densities. And now I want to argue that first of all, this solution remains feasible, and that it exceeds the cost of opt only by a factor of 2. So the factor of 2 is easy to see because well, we are only taking rectangles that are lower than opt's budget, and so we might greedily add up something, we stay below opt's budget, and then we add at most one extra rectangles that means we may overshoot opt's budget by at most opt budgets in addition, so multiplicatively we increase the budget only by a factor of 2 in the worst case. And on the other hand, intuitively this solution also remains feasible because we just shifted the budget down in some sense. So instead of taking rectangles somewhere above, we now take rectangles with the same density as lower. So since all these vertical ray constraints, if they go through some rectangle that opt selected, they will also go through the rectangles that we selected, and we paid at least the same budget on the same density. So in some sense we are still covering all these vertical rays. So this gives us a somewhat simpler solution, which is still too approximate, and now it is important that we can actually guess this solution, and for that, well, in order to reconstruct our solution, this right solution that I pointed out, you just need to know opt's budget. Once you know opt's budget for each of these log n groups, you can immediately recover the solution that I described by greedily selecting rectangles. So we need to guess these log n budget. Naively, this would take n to the log n time, but if you do some smarter guessing where you slightly guess above opt budget, you can even reduce this to a polynomial number of guesses. So there's still a problem because now we need polynomially many guesses for each of these groups. And in total, there can be log n groups because the width of these rectangles, it grows exponentially. And again, everything is polynomially bounded. So this can go on for at most log n layers. But naively applying this to every layer, it would give us a quasi-polynomial many combinations. And in fact, with this approach, you would already get a quasi-polynomial approximation, but we are shooting for a polynomial time approximation, and this again requires some more technical tricks, and I will only briefly give some of the ideas here. So in order to reduce this, the number of guesses for all these, for this solution in total, we will do the following. We let each of these groups of rectangles donate a tiny bit of its budget to the lower rectangle or group of rectangles. So this topmost group of rectangles will give a epsilon fraction to this child, and in fact this other child, which is not drawn here, but which exists in the instance. And these so this increases the cost of the solution only by 1+epsilon, and we will now use this extra budget to buy like a very good rectangles of very good density, so that have a good ratio of cost over weight. So in some sense, if we look at the different densities here for each of these groups, we take the donated budget to buy from some density groups everything that we can get. So until we have used up all this extra budget. So maybe this group of rectangles, it manages to buy like all these density groups. This group of rectangles, it may only be able to buy these two density groups. And on the other hand, these rectangles that we bought extra, they cover all the rays that are covered by rectangles on the group above, because again these rays go vertically to the end. So since we bought some extra rectangles down here, this allows us to forget about rectangles that we bought up here. So in some sense we can throw out some bad density rectangles on the top because we bought some extra rectangles with very good density below. And if you work this out, you can prove that in fact if this middle group, for example, manages to buy all densities up to a certain point, then you are allowed to, we will go to the group above and we will just walk a constant number of densities to the left, and we are able to throw away everything of densities that are worse than this. So there's just like a constant gap here. And of course, these red densities and the green densities are very easy to guess, because in these cases we either take all rectangles, or in the red case we take none of the rectangles. So for these densities we don't need to know the exact budget of opt. And there are still some non-trivial densities where we need to know the exact budget of opt to recover the solution. But if you do the math, there are only log n or order of log n many remaining non-trivial budgets, and this again is something that we can efficiently guess. So using this trick, we throw away a lot of budgets which we don't need to guess, and only log n many budgets end up that have to be guessed. And this makes the total polynomial number of guesses that we need to do to guess the solution for all these parts together. There are some technical details that I hit here, but this is like the intuition behind it. So let me summarize. We use this very nice geometric visualization, which is also greatly inspired by the previous work of Batra, Garg, and Kumar. And this problem of this geometric problem, it's probably one of the nicest, simplest insights of their work and ours, which then leads to this good constant approximation. We, in contrast to them, we lose only a 1+epsilon factor to get this geometric problem, but it also has some new structures like that these rays end up all the way to the bottom, and this allows us, especially this property that the rays go all the way to the bottom, allows us to, in the DP, to avoid a lot of constant at Batra, Garg, and Kumar lost because they didn't have this property. And in the 2 plus epsilon approximation, the factor of 2 that we lose, this is only due to this greedy approach that I explained you a few slides above before, that you may overshoot by factor of 2 to the optimal solution. So this is where we lose the factor of 2. Everything else is just 1 plus epsilon. And for some, it is very plausible that you can also remove this factor of 2. So it would be very nice if you can prove a Peters for this problem. Given that there's a Q Peters, this seems very plausible, but so far we have not managed to avoid this one factor of 2. There are also some other directions, but maybe because of the time, I'll not go into detail and instead let a few minutes for questions. So thank you.
Thanks, Lars. Any question?
Like this, this like guessing technique seems quite interesting. So do you think it has other, like it seems quite nice and like by itself. So do you think it has other applications?
That's a good question. So far, I have not seen other applications, although like a lot of the tricks involved here, like to reduce the number of guesses from quasi-poly to poly. These seem like a lot of these small tricks might be applicable elsewhere, where they might also have appeared elsewhere, to, of course. But like in a lot of cases here, we need to guess budgets, and we need to reduce the number of guesses, and this kind of thing, it might help in other problems also to reduce from quasi-poly to poly, but I don't have any concrete examples.
For my own like deeper understanding, is it like written in an isolated manner, or should I read the whole paper to get this? Like I just want, I mean, I do think there's some maybe in some, yeah, maybe Arindam can speak to it, but like in knapsack problems of this, that have that do require like this density sort of arguments, and there are these budgets. So I mean, it does seem likely. So in your paper, is it written like asking probably a non-technical question, but what's a good way to sort of understand this? Just look at this video again.
Yes, so I think that this talk, like it gives you some of the main intuition, which makes the paper a lot easier to understand if you already have this intuition. Then, of course, the paper is written like in a natural way, that we first define this geometric problem formally, although in the paper we use this somewhat more technical version, which only loses a factor of 1 plus epsilon. So of course this gives some additional complication there, but and then we explain the dynamic program. And
so I guess the question was like many of these scheduling problems, you have this case where you from n to the power log n you get n to the power constant, and there are lemmas, like one is from Chekuri Khanna where they use similar kind of techniques, or there is another lemma on color coding which helps in getting from n to the power log n to n to the power constant. So the question was, are there any separate lemmas where you state, okay, if you have this kind of properties, then I can use these tricks to guess this from n to the power log n to n to the power constant.
Yes, we did separate these kind of like numerical guessing ideas into somewhat general lemmas. So right, so to give you also an idea what the actual properties of the budgets are in order to guess them. So yes, they are separated into isolated lemmas in the paper.
It's very helpful. Yeah. Thanks.
I have a couple of questions. So one is, so for this problem, what is known in the online case?
Yes, in the online case, there cannot be a constant approximation, and I believe there's some, yes, I believe there's some logarithmic approximation. It might also involve like the maximum processing time, so something like logarithm of n times maximum pj. I think this is, if I'm not mistaken, the best online algorithm, and it's also tight. So there's not, in the unweighted case, so if you do just average flow time, it's much easier, and there's actually a constant approximation.
I see. And in the non-preemptive version, what is known, even the offline case?
Yes, I like usually I work a lot of non-preemptive scheduling problems, and in this problem, unfortunately, this is completely hopeless. So there are very strong lower bounds. Even offline, I believe there's not even better than square root n or something like that. So like it looks very bad. Like there are not good algorithms, and there cannot be good algorithms if you don't allow preemption.
And what is known for the Santa Claus variant of this? Let's say wherein to minimize the maximum flow time.
To minimize, wait, this is how is that Santa Claus? So you want to minimize the maximum flow time instead of the sum of flow times, right?
Yeah.
Yes, this is also a very interesting problem that I've thought about a lot. So if you want to minimize the maximum flow time, even without preemption, I mean, with preemption, I think everything is easy. Without preemption, on a single machine, it's again trivial, like earliest release time, first schedule, it's always optimal. Then it's interesting if you look at the setting of multiple machines with minimizing maximum flow time, and there's like also a big gap in our understanding. So for example, in identical machines, we know that there's a 3 approximation, which is just a greedy algorithm, a very easy algorithm. Also, the analysis is not very involved, but we still don't know if there's a PETAS. So it's NP hard for sure, but there might very well be a PETAS for minimizing maximum flow time on multiple identical machines. So that's a very big gap between PETAS and 3 approximation, which would be very nice to resolve.
Thanks. Any other questions? If not, then let's thanks Lars again, and stop the recording.
Thank you very much for inviting me.